Hello, everybody. Today, I would like to do a brief report about our work. Are adversarial examples created equal a learnable weighted minimax risk for robustness under non-uniform attacks? Firstly, please let me introduce the authors. My name is Huiming Zheng from Technical University of Munich, and this is a joint work with Chen Zhu, Professor Tom Goldstein, and Professor Feng Huang from University of Maryland. Now, let's get to our work, and firstly, let's see how our problem is defined. For a given dataset, we might want to find some perfect classifiers to separate the data points into different categories. However, based on current studies, we are able to find strong adversarial examples to corrupt the performance of deep neural networks. For instance, we can find adversarial examples within a norm-based epsilon ball. The hyperparameter epsilon refers to the attack budget of the adversarial attacker. Mathematically, finding adversarial examples could be formulated as solving some optimization problems. For instance, we might want to find the adversarial examples by maximizing the loss function with respect to the perturbations, and the resulted adversarial examples could be represented as the black dots within the circles, like this. As a result, the trained classifier could fail in the presence of the adversarial examples, and in this case, we can say that our classifier is of bad robustness. To solve this problem, we can simply come up with an idea by regarding these adversarial examples as unseen training samples, and just include them into our training process, and this is an empirical defense mechanism and is called adversarial training. One classic training objective could be defined as this minimax game, where we firstly find the worst case perturbations by maximizing the individual loss and then minimizing the overall adversarial risk. With this training objective, we hope that the decision boundary could deform in such a way that the adversarial examples could be correctly classified. It seems that the problem is solved. However, in this work, we argue that the traditional training objective could not handle non-uniform attackers, which I will introduce in the following slides. But before that, let's gather some further intuitions for the traditional setting. The very first observation is that all data points are of different risk and vulnerability by nature. Some of them are far from the decision boundary, but others are not. Therefore, we might ask, is it reasonable to treat all data points equally? Maybe it could be better if we focus more on the data points that are closer to the decision boundary, since they are more vulnerable. And I think this is just like support vector machine, where only support vectors matter. Moreover, in the traditional test phase, it is usually assumed that the attacker will attack all test samples uniformly. That is, the robust accuracy is defined as the expectation of the 1-0 loss taken over a uniform distribution of test data. However, what if the attacker is smart enough to attack the vulnerable samples with higher frequency and higher probability? And in this sense, the traditional metric might be not so appropriate to evaluate the robustness of a trained model. Finally, we have been observing that there could be a uniform trade-off, namely this lambda here, between the clean classification loss and adversarial risk. This lambda, the strength of robustness regularization, is usually manually tuned and is uniform for all data points. Therefore, we might be curious about this question. Is it reasonable to find a more flexible and more individualized trade-off for different data points? So, based on all the observations mentioned just now, we list some problems here we would like to address in this work. Firstly, we should not be treating all data points equally in the context of adversarial training, and the loss function should focus more on the data points that are more vulnerable. Moreover, we also we should also consider the robustness of the trained classifier under non-uniform attacks. Finally, it could be more rational to design a more flexible trade-off, which should be learnable during training, vulnerability-aware, and highly individualized for different data points. All these concerns led us to the idea of reweighting accuracy and robustness for all samples. To express our algorithm more precisely, let's define a term called margin. The margin of a classifier on an example is the difference between the confidence in predicting the correct label and the maximal probability of predicting an incorrect label. Therefore, margin is actually a rather good indicator in terms of predicting vulnerability, since we are making decisions directly based on the margin value. For instance, if a sample is correctly classified and far from the decision boundary, it will have a positive margin, but this margin value gets smaller when the sample gets closer to the decision boundary. On the contrary, when the sample is wrongly classified, it will have a negative margin. Also, we argue that margin is unfortunately accessible to the white box attackers, and this is the prerequisite for an attacker to perform non-uniform attacks, since the attacker knows exactly how vulnerable each data point is. With the definition of margin, now we propose our new training objective, namely the adaptive margin-aware risk. This is a modified minimax risk using an exponential family parameterized by the margin of the adversarial examples generated during training, where alpha here is a positive scaling factor. For a sample with a rather large positive margin, we can say that this sample is far from the decision boundary and is correctly classified. Therefore, it corresponds to a robust data point. We just need to add a small penalty to it during training. When the margin is still positive but relatively smaller, then this sample might be more risky. We might want to add a moderate penalty to it. The worst case scenario is when we have a negative margin, indicating that the sample is wrongly classified and therefore corresponds to a vulnerable data point. So we have to add a large penalty to it. Overall, the intuition behind this training objective is that if the loss of an adversarial example is already large, then the margin-aware weights will exaggerate the penalty even further, and vice versa. Comparing with traditional loss, we can clearly see that the weights are learnable since the parameters of the network theta here is learnable. The hyperparameter alpha describes how much the scaling effect is exaggerated. Moreover, we can also use the lambda as usual, but the trade-off for individual samples are still highly individualized due to the margin weights. Therefore, we can say that our training objective introduces much higher flexibility in terms of reweighting accuracy and robustness. As argued before, if we want to defend against non-uniform attackers, we should not be treating all data points equally. That is, the empirical adversarial risk should not be evaluated over a uniform distribution, where all data points are assumed to be independently and identically distributed. And this ideal assumption is less ideal when we consider adversarial risk, since the data points are of different vulnerability by nature, and the attacker might be non-uniform. Therefore, rational adversarial risk should be defined as the expectation computed over the real distribution of adversarial examples. If we have a closer look at our method, we can clearly see that our objective is actually modifying the distribution over which the risk is evaluated. For instance, if we replace the margin weights with an abstract mapping S, then we can rewrite the objective into a more compact format like this. And if we consider full batch optimization, the loss over the entire training set could be written as the sample mean of individual loss. And based on the IID assumption, this sample mean is actually computing the expected loss over all clean data points. However, recall S is nothing but a learnable scaling factor and is just a random variable conditioned on the parameter of the network. Therefore, it could be absorbed into the distribution. As a result, our modified risk is essentially computing the adversarial risk over the real distribution of adversarial examples instead of clean data points. And this distribution is learnable during training since it is conditioned on the parameters of the neural network. Technically, our method could be plugged into standard adversarial training process by adding extra margin weights into the loss function. And during evaluation, the non-uniform attacker could sample the adversarial examples according to the normalized margin weights. So finally, we can see that it is highly likely that the adversarial examples are generated differently and are sampled non-uniformly. In this sense, we have got some non-uniform attackers to handle, and therefore we need to modify the loss function to defend against such non-uniform attackers. And also, in the context of non-uniform attackers, we are handling much stronger and smarter attackers than usual, since the modified distribution is based on the vulnerability of all test data. The attacker knows exactly how vulnerable each data point is and therefore could sample them with the modified distribution. To fully evaluate our method, we firstly show that the performance on traditional metrics of the trained classifier will not be hurt when using our proposed training objective. In this experiment, we mainly focus on the natural accuracy on clean data and the robust accuracy computed based on the IID assumption, namely this sample mean of 1-0 loss of adversarial examples. And this table shows that we are able to achieve both comparable clean and robust accuracy in comparison to baseline methods like PGD, adversarial training, and trades. Then we show that our method could further increase the robustness of the classifier against non-uniform attacks. For instance, in this work, we evaluated the robustness of the trained classifiers using these two metrics. Both of them could be considered as the robust accuracy under non-uniform attacks, since the normalized margin weights is actually referring to the modified non-uniform distribution. Therefore, we are actually computing the expected accuracy over a non-uniform distribution. The major difference between these two metrics is that the optimal perturbations in the first case are found using unweighted loss, whereas the second one will use the weighted loss to compute the worst case perturbations. As we introduced before, the non-uniform attackers know the margin value of each test sample and therefore know exactly how vulnerable each test data is, indicating that the non-uniform attackers could be much more powerful than the uniform ones, and this could be revealed by the results shown in the table. That is, a ROB is usually much larger than ASA and ATR. Besides, our method could also further increase the robustness against the non-uniform attacks markedly in comparison to baseline methods. Next, we would like to show the effect of reweighting as well. In this experiment, we used different alphas during training. That is, we have different alpha trains, but we tested all trained classifiers using a specific alpha test. And it is to note that the traditional training objective is a limiting case of our method where alpha train equals to 0. And as shown in the table, we can see that with larger alpha, we are able to consistently increase the robustness of the models against non-uniform attackers. Finally, we would like to demonstrate the comparison between our setting and the DRO setting, namely the distributionally robust optimization setting. In the context of DRO, the attacker is not limited to move data points individually, but can move the entire distribution with a limited budget. For instance, we have row here, and the perturbed distribution has to be row close to the original distribution. However, for our setting, there is no limit at all for the attacker to modify the distribution, indicating that our attacker is actually much more powerful. As shown in the figures, we can see that under different distribution budgets, our method is able to achieve both lower loss and higher weighted accuracy than the baseline methods. That's all for my presentation, and I would like to thank you for your attention.